Hello and welcome. My name is Alexander Reiswich and I am a research assistant at the Technical University in Braunschweig. Today I'm going to present you our approach about neural machine translation for semantic-driven Q&A systems and factory planning. But before we start, let's take a brief look at the agenda. First of all, I'm going to explain you our motivation and the research gap of the paper. Second, I will show you the architecture and our developed approach for creating the dataset. Then I will show you the results of the training and validation, and last I will conclude this work and give you a further outlook. So, the current domain of factory planning accesses through a large amount of digital tools that have separate data silos, like shown here on the left-hand side. This is in particular a problem when the planners are searching for information which can be contained in multiple of the data silos, because with every data silo to be searched, the effort will raise for the factory planner. We therefore tackled the approach by developing in previous work a common database which integrates the data for given data silos, and this common database is funding on the semantic web stack. We then further use the database to provide an approach to give role-specific needed information to the planners. This was the first use case, and another use case is to provide a search user interface on the semantic web stack. This is also the topic of this presentation. Here we not wanted just to provide a keyword search, but more complex search possibilities, like providing a question and answering search for the planners. Because there are different approaches for creating Q&A systems, and we have the specific requirement of dealing with a very domain-heavy language in German, and in the field of factory planning, we needed to research and adapt existing approaches in the literature. So, we found in the literature two general approaches for creating a Q&A system. The papers on the left-hand side, they have used an approach where the question is directly assigned to an answer, and the papers on the right-hand side first create a query from the question and then use this query to retrieve the answering information. Moreover, we also categorized the papers which uses a more general knowledge database, like DBpedia, which is a Sparkle database of Wikipedia, and the papers on the bottom, they use a more domain-specific knowledge base. The challenge of our use case was that we are in the field of the factory planning, and the field of the factory planning has a very special domain language. This influenced our approach because we needed to adapt, therefore, our model architecture, which I will talk about in the next slide. A further challenge was to create a proper data set for the training. Here we adapted and extended approaches from Blank et al. And Zong, Blank et al. And Zong et al. So let's take a further look on the architecture. So here the general architecture of our developed sequence-to-sequence model is shown. As I told before, we have a very specific language in the factory planning, and therefore the usage of pre-trained word embeddings was not really possible. So we first tried to use the company wiki, at which we implemented the use case to create an own word vector with the domain-specific language. But we quickly realized that the data was not suited to create an appropriate word vector, because on the one hand, the effort for the data preparation was really high, and on the other hand, the quantity of data in the domain of production in the wiki was not high enough. So we expected to get a word vector with a high bias due to the low data quality and low data quantity also. Therefore, we skipped the word vector and built the translation model as a pure sequence-to-sequence model with bidirectional encoder and an unidirectional decoder. We further used gated recurrent units, 2 layers of it, in the model because the gating mechanisms allowed us to save or drop information between different time steps, which is with the standard RNN layers or units not possible. Besides that, we also needed to develop an approach for the generation of the training data, which I will show next. For the training of the model, we need a data set which contains a pair of a German question and the corresponding Sparkle query to answer the question. We therefore developed this 5-step approach to create the training data out of an ontology which contains the integrated data. In the approach, we first define an ontology which contains the data classes, the object properties, and the data type properties to be extracted from the ontology with the integrated data. In the second step, we use the newly defined ontology in a generic Sparkle query to extract the wanted data into data tables. The data is then further pre-processed via a script to extract the metadata and, if available, the possible data sets for values like, for example, part numbers or part names and so on. We also define templates for select and ask Sparkle queries where the templates have blanks in it where we can then fill the metadata or the values in. And we do this in the 4th step where we randomly insert metadata and also randomly the data values of the extracted data. In the 5th step, we need to pre-process the data. So for the training needed tokens for the start, end, and padding and so on are inserted. The 5th step also contains a manual check and data cleansing for the training data set. This is needed because the ontology with the integrated data can have data samples, for example, with poor data quality, which then can lead to a worse quality of the translation model. We have applied this approach on an ontology that we have had previously integrated for a German car manufacturer and which contains data of bill of materials, working plans, and logistic data. In the next step, we then trained and validated and tested the model. In our use case, the final data set contained approximately 14,000 data samples, and we split them up into 85% for the actual training, 10% for the validation, and 5% for the testing. We considered in our performance evaluation of the model the average precision, the recall, and the F1 score. We ignored the accuracy because our class distribution is very non-uniform, and yes, this can be explained by the fact that Sparkle syntax contains much less identifiers than Sparkle keywords or class or data type or object properties. So for example, an identifier of our ontology is much less uncommon than a select or an ask token in the Sparkle query. So as you can see, the results of the validation that even from a relatively limited data set, a simple Q&A system can be trained. And furthermore, I want to discuss you the generation capabilities of the model on the next slide. For this purpose, I would like to take a look with you at the attention scores of two examples. So in this first example, you can see the attention score, and the attention score shows which token has the highest impact on the resulting query for that question. So you can see here that the token Teilebezeichnung and Gummipuffer, both German words, and there here the query, the data type property and the literal are therefore translated, and both assignments have a very high attention score. So this result is to be expected. The next example, however, a padding token has a very high attention score for the literal value of the query, as you can see here. Here the padding token has a very high attention to this literal, and this obviously shows that not everything is going to be assigned by generalization, but also by bias. And this comes from the limited training dataset, which implies this bias into the model. So to conclude my presentation, we presented an approach for developing translation models for semantic web stack based Q&A systems. We showed that our approach works in a very domain-specific field and with a limited data set. But as with the most models trained on smaller data sets, the model is likely to be biased. So to improve the quality of the model, improvement of the process of creating the data set is therefore needed to gain a larger data set and with maybe more different questions. And in this process, we can also polish our pre-processing, which we saw in our data creation process in step 5. So with that, I want to close my presentation, and I want to thank you for your attention, and I'm looking forward to your questions and your responses. Thank you.